Hello, everybody. Welcome. I'm Bill Tirimanna, and I will elaborate today about innovations in concrete. I hear that you're with about 75 persons in the hall, Sri Lankan engineers. So, yeah, thank you for this opportunity to explain some of our work in the past years. And I will handle 3 topics today. That is starting with high strength concrete. Second is printing of concrete structures. And the third one is floating concrete structures. So if there are really important questions, you may interrupt me and ask Kavish to present the questions. Only if they are short questions. So if you have more elaborate questions about the topics, please wait till the end, and then I will go much further in depth to answer your questions. So the first topic is high strength concrete. Now, in general, concrete qualities are C30 to 37, and you could go up to C250. So those are actually possibilities. So in the first part, it's about 15 slides. I will go into the concrete strength and durability. So precast concrete, site production, also about self-compacting concrete, and yeah, combinations of self-compacting concrete with high-strength concrete. Third part is in the first part I'll also discuss a little bit about recyclable concrete, because in Europe it's now a trend to try to use to recycle material into concrete. So if you're further interested, that's a topic on its own. That's called the undergone project, and where all European countries and universities have collaborated. FDN, our company, is also involved in these projects, and we are doing a few pilots in this year and the coming years with recycled concrete. And that's about nearly 100% recycled material to produce concrete. The second topic is printing of concrete structures. I will start with a more complicated bridge, which we are trying to construct, which we are trying to print. It's a heavy traffic bridge. And yeah, when doing the testing for such a bridge, we of course see possibilities also for printing low-cost houses. So maybe even for developing countries, I'm thinking of Africa and in South America, in some parts of Sri Lanka. This could also be a good implementation possibility for housing structures. The third part is floating concrete structures. We've studied at Delft University and in the company for many years, studies plus application in projects about floating structures. So I will go into a few projects we have already done, like floating breakwaters, and further some development of floating villas. These are like resort projects which we are rolling out. So I will also show some pictures of the possibilities herewith. So to start with requirements and trends for projects in the recent years, we as engineers and contractors, we see a certain trend, and that is our clients are mostly, and by clients I mean governments and municipalities, and people are requiring us to use durable materials. So materials that last for a long time. And also, secondly, they would like to have the material to be low in the CO2 footprint. Further requirement is maintenance-free structures. Like if you see steel structures, every 10 to 15 years, you need to apply a coating on it. Whereas in concrete structures, that is, if of course, designed properly, that is not needed. Further, people require fast building techniques. So precast is very popular, especially in Europe and in the Netherlands. We do about 50% of our constructions in precast, especially floor structures. Further, also for bridge structures, it's all precast beams which are used in most cases. Another requirement is recyclable material, reusable parts for bridges. I'll show an example of a bridge which has been made purely out of reusable parts. So that means that the structure is made in parts for a durability of 100 years, a life expectancy of 100 years. But in the meantime, after 50 years, if the plan changes, you could move the whole bridge and construct a different bridge with using the same parts. So that's also a certain trend which we are observing. And further, with especially with high strength and printable concrete, you have more architectural freedom. So architects also get more possibilities to design according to their fantasies, I would say. Starting with high strength concrete, I will give you here an example of UHPC. UHPC stands for ultra high performance concrete. So when we increase strength of concrete, going from a C30 concrete towards high strength concrete, the durability also becomes much better. So it's more for compact, dense material. So that covering on reinforcement also is much less than using the standard C30 to C35 concrete. So for the high performance concrete, we have produced high performance concrete up to about C220, especially around C200 for the bridges which we have constructed. The tension is around 10 newtons per square millimeter. We have steel fibers in the concrete. Many times we also use stainless steel fibers so that it doesn't rust. Sometimes the normal steel fibers give a bit of rust on the surface. You can use Portland cement, but also high oven flash is also used. And for the higher strength concretes, it's mainly bauxite which is used with a grade of around 3 millimeters to 6 millimeters. And of course, you have to fill in the concrete matrix with microsilica. The weight is around 2,700 kilograms per cube. Here we see some testing. Because for the higher strength concretes, you have to make the mixture yourself. So we are able to make our own mixtures. Depending on each country, we will try to use the available material locally, because there's no point in exporting materials from Europe or from Africa all the way to Asia or to South America. We try to analyze which materials are available and try to crush the material also to the needed size and fabricate the needed strength of the concrete and the durability of the concrete. Here you see the high performance concrete, the C200, which is being tested in the lab in Rotterdam. Here I'm doing the testing with the machine. You see the 200 tons of weight, on the 10 centimeter by 10 centimeter cube of concrete. You see the color is also like a bit of a brown color. It was actually white concrete, which with pigments, we made it into a slightly beige color because the client wanted a bridge in that color. So it's possible to make the higher strength concretes with dark gray or with white microsilica, which actually determines the color of concrete. Here you see the colors which are possible with concrete. This is what we normally show to our clients when they require a bridge. But mainly clients choose for gray, light gray, and sometimes beige or dark gray. So dark gray and light gray are the most popular. I've never had somebody say I want a green colored or red colored bridge, but maybe in the future that will be also asked. Here you see some testing we are doing with high performance concrete. This is a test of a plate which is 40 millimeters thick, and the span is about 5 meters, and we are placing 18 tons of weight in the middle with concrete blocks. So you see the deformation. So actually the very strong concretes react more like steel plates than the traditional concrete. So it's bendable. This is it's bending about 1 meter, you know, the deflection in the middle of the plate. So seeing this, some provinces from the government in the Netherlands, they propose to build lock gates, you know, thin lock gates, which are normally made by wood, in wood. They proposed to make lock gates which are actually maintenance free if you produce them in this kind of high strength concrete. This is actually a C170 quality concrete. Here you see zooming in. And this was also the maximum weight after about 18 tons on a plate of 45 millimeter thickness. And there's also fiber in this mixture. And this was the maximum. After about 6-7 minutes, it collapsed. The plate collapsed in the middle with a hinge in the middle. We videotaped it. So if you go to the FDN group website, you could see the film of collapse. But it took us quite a while to get it to this stage, because you can see how high the plate is placed. It's about 1.5 meters above the ground, because the plate was every time deflecting and reaching the floor. So we had to place it really high so that it was possible to break it in the middle, because every time the plate would deflect and reach the ground and support. This is also a bridge made in Rotterdam, which is demountable. So it's a very flexible structure made out of parts with post-tensioning of the elements together. So it is possible to, to take the bridge apart in a later stage and make the bridge again, maybe even a longer bridge on a different place using the same elements of concrete. So actually we don't have permanent concrete structures, we have more like demountable structures. This is the system. You see the railing elements and the plate elements, and it's post-tension together. The railing is post-tension together to form any length of bridge. By any length, I mean up to like 30 meters length is possible. And then the plates are, we have a special connection with which we place the plates, we bolt them onto the railing. So it's actually like, it's not really a traditional system for concrete. It's a more modern system to make different lengths, different widths. So if you could also make the plate wider so that you will have a wider bridge. This is a photograph of this bridge. It was built in 2013 in Rotterdam, near the center of Rotterdam. And you can also see the color, the dark gray color. That is the typical color of high performance concrete. It's because of the use of the microsilica to fill in the small gaps in the matrix of concrete. And that gives the cement, it's white cement, but it gives the concrete a dark gray color. So if you use white microsilica, the color becomes white, of the concrete becomes white. This is a white colored bridge in Eindhoven. It is actually a pedestrian and cyclist bridge. The span is around 27 meters, and it's about 4 to 5 meters wide. And actually, it was quite a challenge to make this white concrete. I think it's the only white concrete, high performance concrete bridge anywhere. We promised the client to make a beige colored bridge, that means white concrete with a little bit of pigment in it. But it took us about 3 months experimenting with the concrete to get the right color, because the normal concrete was always gray. So we had to do many tests in the lab to be able to get the high strength plus the correct color. Yeah, you all know how architects also are. So they are very determined about certain colors they prescribe. And actually, we made the mistake of promising the client this color, and in the end, it took us much more time and expense to be able to reach the color wanted. Here we see side elements of a bridge, which are very thin. This is the length here of one element is about facade elements, I would say, is about 11 meters, and the height is about 3 meters. And the thickness of such a plate, on the next slide, you will see the thickness. That is 50 millimeters. So it's very thin, slender element. So this is actually, it's like a steel element, which was previously only possible in steel. But with the coming of high performance and high strength concrete, anything made out of steel is possible to be made in concrete. And the reason why the client of this bridge chose for high performance concrete is because of the weight. It was an existing bridge or an existing foundation on which they made the bridge. So they could not use traditional concrete because of weight reasons. You know, then they would have had to extend and reinforce the foundation. Here you see also one of these bridges, the standard bridges, made out of demountable elements in high performance concrete. It's a post-tensioned plate with the side railings bolted onto the concrete, the high performance concrete plate sections. In the core of this plate section is polystyrene. So that also reduces the weight, and the top thickness of the plate is 100 millimeters, and the bottom plate is also 100 millimeters, with in between polystyrene. So if you're using for bridges, even for heavy traffic bridges and other bridges, if you're using high performance concrete, you could reduce the slenderness to about 150, no, about 50 scale, 1/50th of the span is the thickness of the structure. So in traditional concrete, it's about 25. When you use post-tensioning, it goes to about 1/35th. And if you are using high performance concrete, it goes to about 1/50 of the span. So this is a 26-meter bridge with a deck thickness of 400 millimeters. In traditional concrete, it would be like, 800, 900. So it would be about twice the thickness. This is C90-105. It's quite standard in the Netherlands to produce large bridge beams. So this is a bridge beam of 69 meters. This is made by our partner company Heidsma in the Netherlands. They're in the north of the Netherlands, in Groningen. And it's a bridge beam made out of C90-105, weighing about 270 tons for one span of 69 meters. Before, it was only possible up to about 50 meters to make prefabricated beams. 50, 55 meters was the maximum in traditional concrete, going up to C60, 65. But with the coming of C90, 105, or C90 to C105, yeah, the span also increased. These are the different colors you could make in concrete. So if you see red and blues, our clients never ask for these colors. They normally ask for this gray colored or beige white colored, or on the right side, this is also a bit of a beige color concrete. And when you polish it, it becomes like this. It's like a marbled floor. So you could make quite yeah, beautiful structures in the new concrete types, using, of course, different aggregates which you can polish. Here you see, these are quite standard concrete. This is actually a bit of a high strength concrete color, the dark gray, and light colors. And here you use special aggregates to be able to polish the concrete. So especially for smaller bridges, this is beautiful, but for large bridges, it's not economical to do this. So then you just use, without any polishing, you use the bridge. Okay, so that was about the concrete, and now I'll go over to the 3D concrete printing. That's the second part. So we started, yeah, actually doing some research into concrete printing after we received an assignment to build a bridge. And that was not a small pedestrian bridge, but it was a heavy traffic bridge of 30 meters length and about 8 meters width. So we started our research about 3 years ago, and we concentrated, we worked with different universities, and we concentrated on application of the layers of concrete, the allowed material strength, the reinforcement, how to reinforce such a printed structure, what is the durability. I mean, it's nice to print a bridge, but if it fails in about 1 year time, there's no point in doing such a thing. And also we concentrated on what price is possible for such a bridge. You know, it always with civil structures, it has to be economical, otherwise the client is not prepared to give you the assignment. So here we see we are experimenting with a printer. What is a printer? Actually, it's a pump for concrete. So I think about 5 to 6 years ago, people started to produce printers. You see the nozzle. This is at the Technical University of Eindhoven, where we are printing. You see the client is standing here, scratching his head and thinking what we are trying to do. So we are just printing a small arch bridge beam here of a length of about 4 to 5 meters, just to do some experiments. So we print something, and then we put some preloading on it and see how it behaves. Because we could, of course, as engineers, we are all able to do finite element analysis and you know, judge what is allowed. But when you're doing something for the first time, the testing is really required. So every time we do tests and try to find out in our finite element models what is exactly happening. Here you see the printer. This is a portal printer. So there's a nozzle like on the right hand side, and it's a portal, so it can move around. So it's actually a 2D printer. It's not 3D, it's a 2D printer. We can print something on a flat surface. So we had to use this possibility to be able to print a bridge beam. Here you see some designs made by our architect for a bridge. bridge with a span of, here I think she has drawn a bridge about 10 to 15 meter span. And so we were actually analyzing different possibilities for a bridge in printed concrete. So very quickly we came on to, you know, because the concrete cannot be reinforced properly, we came on to the compression force. So that means arches, like Roman arches, which we wanted to print to be able to resist the heavy forces. So it's not the loads were also huge. It's a heavy traffic, so you have to comply to the Eurocode loads, the load sets. So it was, and you have to guarantee the bridge also for 80 years, 80 to 100 years. So it was in reasonable time. We figured out that it's not possible to make very complicated structures, but we'll have to go back to traditional method of making a concrete arch. So to print a concrete arch to do this. Here you see the structure. It's an arch. And what we are actually trying to do here is to print the whole structure. So this is the length of the bridge is 30 meters. Is it exact? Yeah, 30 meters. And you see the foundation piles going in. So only the foundation piles would be steel piles or concrete piles are made traditionally. The rest of the structure is fully printed. But printed means prefabricated. Printed in a print center with a printer indoors and then transported to location to be able to place on site. Here you see us printing one beam. And the printer could not place reinforcement. It could, with its nozzle, it could push through, you know, pump a little, what do you call it, a wire, a steel wire, but that's not sufficient. In concrete structures, you need a few % of reinforcement. So what we did was, to make this bridge, to make this bridge beam actually, we printed layers, and then by hand we placed a concrete rebar on it, on top of the layer, and then printed the layer on top. So like that we built up layers, so up to about 30 to 50 centimeters height, we could make a bridge beam flat on the floor. So here we are actually on the left, you can see this is half an arch. So we are printing this, as you saw before. That is this arch we are printing. And then here there's a flexible connection, which we connect to the other beam with high performance concrete. So it's an on-site connection of the two arches. Here you see it. So actually, yeah, this is actually not, it's not very good. In the case that we have a concrete printer, we would like to print the whole thing out three-dimensionally. That's not possible at this moment anywhere in the world. It's not possible. And we are by hand placing reinforcement to get the strength necessary to fulfill regulations and requirements for this bridge. So in the future, of course, this person will be replaced by some robot who is going to place this reinforcement. But for now, we have to place this by hand. So it's very intensive work. So we need about 4 to 5 persons who are manufacturing this. So then you would ask, so why do you print it? You could also do this traditionally if you need so many people to work on it, you know. So the printing is actually profitable if it's only the printer that is doing the job and not having many persons, laborers, work next to the printer. Here you see half a bridge beam which we have printed. This length is about 6-7 meters. And here you see the layer with the placed reinforcement. And then on top, we print again another layer of concrete. So like that we go on. After printing every layer, we place reinforcement. And here is the connection. You see there's reinforcement sticking out of the printed beam so that we could make a connection between the two beam halves. between the two arch halves. Here we are lifting the part of the concrete out of the printer to place it somewhere else and to print the next half. Here I'm actually standing next to a fully printed beam with the connection in the middle. And we are trying to do some load tests on this beam. So this is the method to print a 20 to 30 meter length bridge by printing half the size of the necessary beam and then connecting on site these two together. So you may ask me, yeah, okay, why did you make such a small element? Yeah, that's because the printer couldn't handle any larger elements. It's purely depending on the portal of the printer, how far it could go and how much space you have. So for 2 years ago, this was the largest printer available in Europe. Now there are some printers which are a bit bigger, but not much bigger. So you cannot print like a 20 to 30 meter bridge part in one go by one printer. It's not possible. You have to make them in parts. Here you see the connection. Here the connection of the two parts to pour the high strength concrete and to connect to each other. Oops, sorry. Oh, I'm going the wrong way, I think. Yeah. Here you see the end result of the bridge, which is still, yeah, we finished the research, but now we start with making the real bridge. So actually this has not started yet. We have finished the research in the beginning of this year. We finished 2020, we finished all research, especially durability problems which we had. And now we could start with production of the bridge. It will be about a 30 meter length, fully printed bridge. That means foundation, except for the foundation piles, is printed. Yeah, here you see another printer. This is like a printer with an arm. This is in France. They can print these structures on site. So that's also a new possibility. Instead of just prefab, you could bring the printing robot to location. You can see it has wheels, yeah, what do you call it, like a tanker, the wheel, and you could bring it to site and print structures. Here we are doing some experiment. This was in France. So while doing all this, as I mentioned before, we came to the conclusion that, yeah, it's also very interesting to build houses in concrete. Now, if you see for housing, the walls, they don't require so much, you know, strength. So for bridges, especially for the heavy duty, heavy traffic bridges, it's a different story. So a good idea would be to print houses, especially in countries where social housing is needed. You could have a printer which can be transported and placed on location. And I think the speed should be about one house in about 2 days that you could print it. Here you see the possibility. This is unreinforced concrete, print layer on top of each other. It's when you cut this, if you do a cut in between, you see that it's very homogeneous as long as you print it in a certain tempo. So if the printer breaks down, it becomes a big problem. So you need yeah, very efficient and reliable printing materials, a reliable printer to do this. And for the European countries, you could put insulation in between here. But for tropical countries, that's not needed. This is one of our partner companies in Belgium. They have just printed a house. So actually, when you say print a house, means that they have printed the walls and the partition walls of the house. The roof is not yet possible in printing concrete. You could make something like an arch, but at this moment, it's not done so much. And it also has to do with the architectural presence of the house. People prefer a flat roof, and that's only possible up till now with with wood or some other material. In printing concrete, it's possible, but then you'll have to put post-tensioning and have some elements post-tension to each other. But this house was built about a few weeks ago. They finished it. Yeah, here you see again, actually the same slide, but then it's cut in the middle, and you see the insulation which is possible with printed concrete. And the strength of this concrete is around C30 to C40, but printed concrete goes up to C90. So it's possible, but then the color becomes more dark gray. It's possible to get concrete C90 printed. So for housing, it's perfect. You don't need more than that. This is a house printed in California by another group. This is not done by us. They have a special printer which you could buy, and you could print circular buildings. And yeah, you can see the windows are all by wood, the door also, but the rest is printed. So such a house is printed in about 2 days, they say. But of course, it's only possible if the printer works properly. So that needs a bit of startup. But once the printer has lost his startup problems, it should be possible to print in a few days. Here you see in El Salvador, I think it was a Swiss engineer who has designed and made a whole, a small village with printed houses. So this is interesting especially for developing countries which a big need for housing projects, just to build, not for the large villas, but for the small houses. You just need a few walls, few rooms, and a roof, and the quality of your life becomes much better compared to the slums and things which still exist up to today. And to go back to the previous slide, the price of the house should be below 3,000 to 4,000 euros. So that's about the going price for a small house, 55 square meters, and so 500 square feet, 500 to 600 square feet. That is the budget that people are able to pay. So that was printing concrete. Now I'll come to the last chapter, that is the floating concrete structures. This was actually one of the topics we researched for really a long period, and we have built many structures around the world, especially floating breakwaters, and then you have floating marinas and cruise terminals. Also floating buildings in the sense of hotels and offices and houses, recreational villas. In the end of this, I will show some projects which we are proposing for Sri Lanka, for a client in Sri Lanka to build, resort villas in concrete, floating concrete. Yeah, these are actually the 6 methods of building floating structures. You have the typical boat structure in concrete. This is the traditional floating structure which you have in Amsterdam in the canals. On top of this left upper hull structure like a boat, they built with wood, a low weight house on top. And this will be the cellar. You could put some bedrooms in here. Sometimes there are some windows at this level. And then there's a wooden floor or a steel floor on which you could build up to about 2 stories. 2 to 3 stories could be built on this. The other ones are, the upside down hull with the air cushion here. This is many times used in the offshore. Further, you have compartments because of, it's possible that it gets knocked by a ship or something, but if it's in protected area, this is not necessary. And the other one is just polystyrene and a concrete layer on top of it. This is also used many times. Here you see steel pipes on top with concrete. So those are some methods of construction. If you have floating structures, you many times have these loadings. I won't go into this at this moment because it will take a long time. But if you are interested, you could always send me an email. I can go further on the engineering aspects of floating structures, because it's a little bit more complicated in the sense that it's more of a dynamic loading on these structures. And many civil engineers are very fond of static structures. So when it comes to dynamics, it's a bit, yeah, it's more the mechanical engineer and the shipbuilders territorium. But it's still possible. There's a lot of experience in this, and there are also many design codes to be able to build concrete floating structures. Here you see the typical representation, the mechanical representation of a floating structure with its influence zone around, with the anchoring and the incoming waves that creates actually movements of the floating structure. Here we are simulating, actually, this is a floating breakwater. In the past, you had to always do tests at the hydraulic lab, like the Lanka Hydraulic Institute. But nowadays, many tests are first done, especially for smaller projects. It's always done only with simulation. So we have hydraulic Delfrac simulation packets where we can simulate the waves and then put the structure and analyze its movements according to its design. And of course, for some important projects, we also have to do the hydraulic basin tests. So, but that's actually just for confirmation of the results which we have achieved with the computer simulations. Yeah, here are some structures built in Amsterdam. This was in 2002. We built this. It's about 3,000 square meters of floating structure in the actually near the center of Amsterdam. So this is all possible. So especially countries with a lot of water and rivers and lakes, these are good possibilities to exploit that surface. Here's in the south of the Netherlands, a building of with a length of about 70 meters by 5 meters width. It's like a harbor office with hairdressers, there's a library in the cellar, etc. So it's quite a large building which is floating. And you would ask, yeah, then is it economical to have a floating structure? Yes, it is. But only people are not well known with it. So people choose in the industry for existing solutions, but these are all possible solutions. Of course, if you're making large floating structures, you need a dock. This is the largest dock we could find in Europe was in Ukraine. And you could build up to 60 meters width and 350 meters length. You could build one concrete section. So that's quite a unique thing because they are building naval ships for Russia. And and they have started about 50 years ago building also concrete docks. So that's the largest place you could build something. And then by sea, you could tow such a structure anywhere in the world. This is a design we have made. This is actually made for Sri Lanka. This is a floating villa. It's for a resort hotel. And you could see it's made out of concrete C90 105 with thin walls, total floating, and with the quality of the pictures are not so good here as they are not definite yet. But we plan to make it definite. But yeah, with the Corona crisis at this moment, things have been postponed. But I'll be back there soon to be able to promote this. So coming to the conclusion, what we say is that we have done many tests and we have gained a lot of knowledge which we would like to share with also other engineers and other companies. So we do invite you to contact us for this. all the topics and projects of the past 10 years. We have made a book. It's in English. It's about all these innovative projects which we have also completed. So it's not only research, some topics are only research, but others are also application and construction, and all calculations are also in this. So we would like to, it's not a very commercial thing, but we would like to know if people are interested so that they could send me an email or through LinkedIn, connect and show interest so that we know how much copies we should print. So please let us know about it. So there are two points. That is the book, if you want it, and the other one is application of these technologies. We are searching for partners all over the world. I think there are some people also from South America connected today. We would like to, especially Sri Lanka or in Suriname, apply these technologies. So we are searching for partner companies, especially contractors who are in construction, to be able to collaborate with. Thank you.